Pink booklet, section 13, moments, questions 10 and 11. So, in the diagram of the crane below, calculate the pulling force needed to keep the jib horizontal. So, what we've got here is a load. That load is acting down that way, so that will topple this crane in this direction. Okay, downwards. So, in order to stop that happening, you have a counterbalance here, and this is caused by motors and gears in here and a pulling force. So they will act in the opposite direction. So let's have a look then. In the diagram of the crane below, calculate the pulling force needed to keep the jib horizontal. So this force is pulling this around this in this direction downwards, about this point here, the pivot, and that must mean the other force is acting downwards here, about that pivot. Okay, now quite clearly, if we take this about this force acting downwards here about this pivot, we can see that that is the clockwise motion or clockwise moment. This acting in this direction about this pivot here would be the anti-clockwise moment. Now we know from our principle of moments that the anti-clockwise moment is equal to the clockwise moment. So we need to find the calculate the pulling force needed to keep the jib horizontal. So what we're doing here is finding the pulling force here. So our anti-clockwise moment then, let's have a look what we've got then. We've got force times some distance, and our distance is here 2.4 meters, and that's equal to the clockwise moment here of the force of 6,000 newtons times this distance here, 6.4. So quite straightforward then. What we need to do is we need to make force of the anti-clockwise moment of the subject. So if we divide both sides by 2.4, we can see that force is going to be equal to 6,000 times 6.4 divided by 2.4, which I believe is 1600 newtons. Okay, now if we look at this one then, just to double check, so we've got quite a bigger distance. So for the anti-clockwise and clockwise moments, then you've got force times distance and force times distance here. So for them to be equal, if one of the distances is greater, the force must be less, and vice versa. So we've got big distance, small force. Here we've got small distance, so we must have big force. And as we can see, it's a bigger force than this one here. So we must be in the right ballpark there. Now, moving on to this last one. So, in the diagram below, the weight W has a mass of 300 grams. Calculate the load needed to balance the system if the load. Calculate the load needed to balance the system if the load is 20 centimeters from the pivot and W is 72 centimeters from the pivot. Okay, use N is 9.8. So we've got a weight here of 300 grams. So this is actually the mass of this weight here. To find its weight then, what we need to do is we will need to take, well, weight is equal to mass times gravity, which is why we've been given this. So we've now got mass, which is 300. No, it isn't. It's equal to, well, that's 300 grams, that's 0.3 times 9.8, which will give me 2.94. So I've actually got a weight of 2.4 newtons here. So In the diagram below, the weight has a mass of 300 grams. Calculate the load needed to balance the system. If the load, which is here, is 20 centimeters away from the pivot, so that is 20 centimeters from the pivot, and W, which is the weight, is 72 centimeters from the pivot. So what we've got then is, if this is acting downwards about this pivot here, then this would be the anti-clockwise moment. Now, in order to balance that, then the load must be acting in the opposite direction about the pivot, which it is. So that is the clockwise moment. So we now need to find the load needed to balance this weight. So we need to find the force acting in the clockwise moment. So, right, anti-clockwise moment then, from principle of moments. Anti-clockwise moment is equal to clockwise moment. So let's have a look. We've got 72 centimeters. Now we could work this out in Newton centimeters, but that would give us, that wouldn't allow us to work things out in newtons. So what we need to do is we need to take these 72 centimeters and convert it to meters. So 72 centimeters is 0.72 and 20 centimeters is 0.2. So we've got anti-clockwise moment, so we've got 0.72 times the distance, times the force, which is 2.94, and that's equal to the load, which is our force in the clockwise direction, times the distance, which is 0.2. So our force, so if I want to make F on this side the subject, I can divide both sides by 0.2, and that will leave us with 0.72 times 2.94 divided by 0.2, and that will equal force, which I believe is 10.584. That tells me here to do two significant figures, so I'm going to round that up to 11 newtons. So our answer on here is 11 newtons.